Hi, we're Tomorrow Lab,
an invention studio focused on new hardware technology
for big brands,
agencies, and startups. We create prototypes
and then turn them into market-ready, manufacturable products.
On Potentially Genius, we take a potentially genius idea
and turn it into a potentially genius thing,
using components from Digi-Key's massive library,
all while giving you a peek into our 4-phase invention process.
In this episode, we're meeting with Enda Nicholl from Analog Devices. They're showing us the ADMT4000 Multiturn Sensor.
So, Enda, tell us about the sensor you brought us.
We brought you the world's first multi-turn position sensor in one chip. It's the ADMT4000. If you're going looking for a position sensor in the marketplace today, you'll find Hall effect magnetoresistive sensors. You'll find optical encoders, resolvers, inductive solutions, and so on and so forth. But what you'll notice is they all have an absolute measurement range limited to one turn. So when you get to 360 degrees, you go back to zero. So you know if you've got a system where there's more than one turn of motion and you lose power, then you've no idea where you are because you've lost that position. You know within one turn where you are, but you don't know where you are within multiple turns. But with the ADMT4000, it tracks all that motion without any electrical power or any mechanical contact, as well as contactless and powerless. So it is really unique and a game changer in the whole field of position sensing. And accurate to 0.25 degree over 46 turns, that's pretty good resolution, right? You know, so it's great technology. We're seeing new applications every week, and you know, and I think I'm looking forward to what you guys come up with.
So we wanted to show off 3 features of this sensor. First, that it's very accurate. Second, that it can count a lot of turns. And last, that it knows exactly where it is, even if you power it off and power it on again. So we had 3 ideas to show off the features of the sensor. The first was a smart seatbelt for cars, something that could detect occupants when they put on their seatbelt and classify them by how long the seatbelt stretched. The second was a door open counter for access control auditing. Basically, if you had like a special panel somewhere on an industrial site and you want to know if it's been opened and how many times someone's accessed it. And the last, we like this idea of a cheap giant set of calipers. We have lots of calipers at Tomorrow Lab. They're all too small to measure some of the bigger things that we need to measure. So we're using tape measures, which are not very accurate. So the idea of having some big calipers, it's fun, but it's also possibly very useful for us.
To prototype the device, we're ordering a microcontroller, a 3.3 volt regulator, a LiPo battery charger and regulator, a momentary switch, and an on-off switch.
So we're making giant calipers. Small calipers here slide back and forth. So we need a way to make something large slide back and forth. And I hear you ordered some parts from Open Builds.
Yeah, I looked at Open Builds. They have a lot of example assemblies on their page, and so we're going to take some inspiration from one of their assemblies, which includes this 2060 V-slot gantry system. And so this is the gantry plate, and this is the 2060. It's just going to slide linearly with some V-wheels.
And what are these for?
These are going to hold the plate on the track smoothly, and then one of them we're going to edit so that it fits our sensor.
Before you get into that, the wheels, how do you, I assume they have to be dialed in so that they grip the track just the right amount. Because if it's too much, the bearings will overload and it'll be ga, ga, ga. And it's not, it'll rattle and then we won't get good readings.
That's just right. This eccentric nut part has an off-center bore through the middle. So we can change its rotation, and that moves the wheels closer or further, and we can dial in exactly how tightly the cart grips the rail.
Hey Dylan, I just worked on designing our linear system. Could you tell me a little more about this magnet and how I can integrate that into our gantry?
Sure. So basically the way the sensor works is that a magnet is suspended over the sensor itself. And inside the chip is actually a spiral of magnetic material that acts as the turn counter. So as you actually turn the magnet over the chip, you are magnetizing and demagnetizing parts of the spiral. And the great thing about this sensor is that when we cut the power, those magnetic tracks will still retain the information about how many turns have been done, and then we can go right back to measuring the exact value. So this is the visual indicator. We haven't converted this angle into a distance yet since we haven't built the calipers, but essentially what we're doing is we're turning that turn count into a total number of degrees that the sensor has been turned. To use the sensor properly, we just need to keep the magnet about 20 millimeters over the sensor and vertically aligned with the sensor.
Cool, I'll keep that in mind when I'm aligning our wheels and our sensor.
Okay, so now that we prove the motion system works, we have to add the sensor wheel. And we got the hole drilled, but we did order some parts, and it's time to see if it works. So you printed this great connection for a V wheel with some 3D printed parts. Do you want to press that together and see if it becomes one solid wheel?
Yeah, so one side holds the shoulder bolt. It goes in, and it should press fit. Nice.
So the point of this is to make a wheel where the shaft spins with it.
It's like a rigid system now.
And that's different from this kind of wheel, this kind of wheel, where it spins around the shaft. Because we want to transfer the rotation of this wheel up through the mounting plate and be able to sense it with our sensor. So let's see. Okay, we have 2 static idler wheels and 1 wheel that spins through this shaft. So let's see if it fits on the rail.
Nice.
So now when this slides back and forth, we do see the bearing spinning, which means we have rotation from the friction wheel through the plate to the nut on top. So if we can glue a magnet on the top of this, we should be able to sense the rotation of that magnet with the circuitry that Dylan made and build a sensor board on top of this. I've done a bunch of CAD, and I wanted to see how the jaws felt in real life before I go and build them out of wood. So I mocked them up in foam core just to get a sense of the scale, and it's pretty cool. So just the platform here, this slides back and forth. When this slides through, we can measure internal diameters or external here.
Nice.
This sliding carriage has a dimetric magnet on it. The poles alternate around the circumference of the magnet instead of being top and bottom. So as the magnet spins, our sensor can detect its changing position. And it rotates along with the sliding of the carriage.
Here's the actual chip that senses the magnetic field, and that gets mounted and positioned
Here, just with this mounting plate.
over like that on top of the magnet.
Yep. So next I'm going to actually cut these out of plywood. So I 3D printed this housing, and I made space for all of the electronic components you gave me. Do you want to talk through where everything ended up and what it's doing?
Sure. So here's the 7-segment display, and we're feeding data and clock lines to it, as well as power. Here we have the battery charging board, and that uses our LiPo battery. And to power on and off the device, we have our power switch here and a momentary switch for zeroing the calipers.
And all of that is wired to these components inside here.
Right, so we have the microcontroller 3.3 volt regulator for the development board and the sensor development board itself.
So all we have left to do is close this up.
Yep.
Hey, Enda, it's good to see you again.
Hi guys, I'd love to see what you've done with the ADMT4000.
We've been having a lot of fun coming up with ideas of what we could make with the multi-turn sensor.
This is X-CALIPER. It's a very large pair of digital calipers based on the ADMT4000 Multiturn magnetic sensor. Like small calipers, we have a switch to turn them on and off, a button to zero the reading, and an LED display that shows the measurement, exclusively in millimeters. These calipers maintain their position even when powered off. Like small calipers, it uses a set of jaws to measure both the inner and outer diameter of various objects. So now we can measure all sorts of large and irregular objects around our neighborhood that we've been wondering about.
Oh, wow. I love it. I love it. I want one of these myself. Yeah, you know, and I never thought of a large calipers like that. I only related to the small handheld one that you have in, you know, in the machine shop or whatever, but never thought to scale that up. So it's novel, it's new, it's exciting, it's practical, you know. So there's definitely a market there for it, I would say, guys. And it's a brilliant idea, and to execute it, so the engineering involved in getting it to a workable model like that in such a short time frame was phenomenal as well. So that's congratulations and well done all around. And it's a great platform to show off the ADMT4000. Absolutely genius. You know, just I know I didn't think of something like that myself, so you got there before me. So well done, guys. Jesus, it's brilliant.
Thank you so much for watching, and thank you to our friends at Digi-Key. Please be sure to visit the Digi-Key YouTube channel to see our past episodes.